Now you might say, well, Daddy, 1 to any power is just 1. You are mistaken, my boy. Good morning, fellow mathematicians, welcome back to another video. Today's video is extremely exciting in my opinion, and it's extremely hot in here, so it's going to get really sweaty daddy. That actually rhymed, that's so disgusting. This right here is once again a prerequisite video, and we are going to talk about one pretty dope addition theorem in my opinion. So we have this finite product here of sine waves, and it's going to evaluate to something you are probably not going to expect, and it has to do a lot with abstract algebra or algebra overall. So we are going to give it a shot. So at first I would like to rewrite the sine as being its exponential complex exponential form, so negative I over 2 times this e to the something stuff. Okay, so this thing right here is just our product, our finite boy of, okay, we have negative I over 2. Some people like to use 1 over 2i, but that's equivalent. And then we have e to the I, this argument right here, pi s over k, minus the very same thing, but with a negative sign up here in the exponent, okay? Now, what can we do next? Well, next I would like to distribute the negative sign into here and also bring this I over 2 to the outside, okay? Meaning, in here we are going to change our order, basically. Now we are going to bring I over 2 to the outside. You have to imagine it this way. This thing right here, this I over 2 is actually glued to this part, which is dependent on s, meaning we have, for example, our first member here times I over 2, then times the second member times I over 2 times the blah 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 up until times the k minus 1th member times I over 2. Meaning overall, if we want to drag this to the front, we actually have to take this multiplied by itself k minus 1 times, meaning I over 2 to the k minus 1th power, okay? This is what is going to happen. Now, what are we going to get? We are going to get I over 2 to the k minus 1th power. Try it out for yourself. Take a piece of paper. It's actually pretty easy what I just said. And then also times our finite boy. And then we are going to get this right here, okay? E to the negative I pi s over k, and then minus e to the I pi s over k. Now, how can we proceed? Well, next I would like to get rid of this thing right here, okay? I kind of want to drag it to the outside too. Or rather, we would like to break this product up. Now, why not factor this thing out right here, okay? If we drag this to the outside as a common factor, we are going to get a 1 right here. This was this originally. But if we drag this to the outside, this thing right here is just 1 over this term. So in order for us to get back to this term, we have to have this term twice squared, okay? Because if we multiply this in, we are going to get rid of this over this, which is nothing but a 1, which is the coefficient here, you could say. So we are going to get I 2 times pi s over k. I hope this did make sense. Now we are going to break this up. This thing right here is just the product of this times the product of this. Both are dependent on s. Now, what is going to happen if we take the product of this thing right here of e to the negative I something? Well, if we take a look at e to the a times e to the b, that's a nice functional equation in the real and complex numbers. It's going to give us e to the a plus b. Meaning, if we are going to multiply k members, k minus 1 members of this thing right here together, then we can basically bring this product to the inside, to the argument, and it's going to turn into a sum. This is just how this functional equation works. Meaning we are going to get I over 2 to the k minus 1th power. Then we are going to get, I'm going to write it like this, exp, just the exponential function right here, because it's easier to write this way. Then we are going to get negative I pi 1 over k. Okay, I'm dragging all the stuff that's independent of s to the outside. And then, like I said, we are going to have the summation from s being equal to 1. It's going to run over the same indices right here, to k minus 1 of just s. And also we are going to get this finite product once again to k minus 1 of 1 minus e to the I 2 pi s over k. This thing right here is really special. We have to talk about this thing right here in a minute. But at first let us see what this right here is. For this, I would like to give a little example. What happens if you have the sum from 1 to infinity, for example, negative 112? That's such a bad joke. That's such a bad joke. We don't do this here on this channel anymore. We are through with the minus 112 stuff after doing the math snack. So imagine you have a sum running from 1 to 3. Okay, so this is going to give you 1 plus 2 plus 3, 6. But what is 6 exactly? 6 is nothing but 3 times 4 over 2, 12 over 2. 4 is nothing but 3 plus 1. This thing right here is what you call the little Gauss theorem. Okay, there's a nice little story surrounding this right here, a nice little myth, a nice little filthy Frank law. This overall is going to evaluate to, in a normal case, if you have the sum from 1 to k, you are going to get k times k plus 1 over 2, just what we said, 3 plus 4 over 2. But right here we have it to k minus 1, meaning this thing right here, if we transform it, it's going to give us, okay, this is going to be k, then times k minus 1 over 2. I hope you can see where this came from. Okay, just a nice little explanation right here, meaning this k and this 1 over k is going to cancel out to be 1. Then we are just going to have this chunk right here. Okay, I'm going to write it out. We are going to get I over 2 to the k minus 1th power. Also we are going to have e to the, okay, I'm going to put it like this. We are going to have negative I pi over 2 times k minus 1. Okay, this is just same thing times our product right here that we have. Okay, now how can we continue from here? Well, one little thing I want you guys to notice is that if you have e to the a times b, that's the same as e to the a to the bth power. So we can have some YouTube drama here, some YouTube beef, okay? Meaning this thing right here is actually e to the negative I times pi over 2 to the k minus 1th power, okay? We can just raise it to this power. I want you guys to notice that this power and this power are completely the same. But what exactly is this? Okay, e to the negative I pi over 2. Well, if we take a look at the complex plane and the principal branch at that's just the little principal branch. If we go negative pi over 2 downwards, we are going to land at negative I. This thing right here, this is actually nothing but negative I to the k minus 1th power. Leaving us with, if we bring those two together, so dragging the k minus 1th power to the outside, we are going to get negative I times I over 2 to the k minus 1th power times this product that we have. So 1 minus e to the I 2 pi over k times s. I'm going to put it like this for reasons that will become apparent in a minute. Okay. Now, what is I times I? I times I is negative 1. Negative 1 times negative 1 in any field is nothing but 1. Okay, negative times negative is positive. I made a proof on that. Check it out. So this thing right here is actually 1/2 to the k minus 1th power. Okay? So we can rewrite this as 1 over 2 to the k minus 1th power. Now, this next part is going to be quite algebra heavy. We have to talk about the roots of unity, of the cave decree, the cave roots of unity. If you never heard about that, that's not a problem. We are going to give it a shot in a second. Give me a second. So what exactly are those mathematical roots of unity I was talking about? Well, they are just the simple solution to the polynomial x to the kth power minus 1. And if you ever did any algebra, linear algebra, you are immediately going to see that this right here is just a polynomial in terms of its linear factors. If you never did any algebra before, we are going to go through it with 1 or 2 examples, because people just love examples. They don't like the abstract, they just love examples. For this, I would just like to take a look at something we have derived before. Namely, if we take a look at a simple polynomial, being equal to 0 to k, or we are going to say n right now. This thing right here is nothing but 1 plus x plus plus x to the nth power. So this thing is just a monic polynomial of the nth degree. Okay, as simple as that. But we have derived an even nicer form of this, doing some little algebraic manipulations. That's just a finite geometric series, you could say, meaning this is nothing but 1 minus x to the n plus 1th power over 1 minus x. Now I would like to bring this into a form to k minus 1, okay, just for this reason right here, because our product actually runs to k minus 1. Meaning if we let n transform to be k minus 1, okay, this just runs to k minus 1. Also this is going to be k minus 1 plus 1, which is nothing but to the kth power. Now, what I would also like to do is to factor out a negative 1 in the numerator and denominator. Negative times negative is just positive. So that's the same as saying we have x to the kth power minus 1 over x minus 1. And what we want to do now is find the roots of this polynomial right here. Okay, this is just some simple polynomial, and what we can do, we can find the roots of this thing. Because there's something really dope in algebra that tells you, maybe you know what it is, if you find out all the roots of a nth degree polynomial, for example, you can actually decompose this into the multiplication of its n linear factors. Okay, this is what algebra tells us. Now, if we want this to be equal to 0, what's the one condition? Well, x can be whatever it is, but infinity is not a number right here, okay? Meaning this thing can only be 0 if and only if x to the k minus 1 is nothing but 0, okay? That's exactly the case if x to the k minus 1th power is equal to 0. It's just what it is. Meaning we can solve for 1, okay? We can solve for x, I'm terribly sorry. Meaning if we add 1 on both sides and then take the kth root of this thing, we are going to end up with all the roots of x. So from s being equal to 1 to k in this case, or we can say from 0 to k minus 1, really doesn't quite matter what you have right here. This is nothing but 1 to the 1 over kth power. Now you might say, well, Daddy, 1 to any power is just 1. You are mistaken, my boy. This is not the case, okay? Not always, at least. So you have to remember what a 1 actually is. If we take a look at the complex plane, the 1 is right here, okay? 1, okay, is just 1 to the 0th power, for example, but it's also e to the I 2 pi. But it's also e to the I 4 pi, and so on. Okay, so this thing, this 1, is nothing but e to the I 2 pi times s, okay, doing rotations right here, over our k, where s is just some integer, for example, which it definitely is, because we are going to run over this index right here, depending on our roots. Okay, so if we plug 0 into here, that's just a simple 1, e to the 0th power, but it can get worse. So how can we put this into examples, for example? How can we put this into examples, for example? Let's take a look at a really simple example. For example, what the fuck am I even saying right here? X squared minus 1, okay? We all know that we can solve for our x right here, with x being nothing but positive or negative 1, taking the square root, okay? Easy as that. But also, this thing right here is nothing but the difference of two squares, meaning we can actually simply decompose this thing right here into x minus 1 times x plus 1, okay? Being equal to 0. We can decompose this. This thing right here is just our polynomial that we had right here, and we know what the roots are, namely our positive 1 is in here and our negative 1 is in here. Negative becomes positive. If we have a polynomial and we decompose it into linear factors, it's going to look like this. F of x is then going to be x minus the 0th root times dot 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 up until x minus the nth root in this case, depending on your polynomial, okay? This is what we can do with polynomials. Those are the roots right here, x0, x1, xn, whatsoever. Those are actually n plus 1 degree polynomials. That's why I put the index from 0 to k minus 1, because we actually have a kth degree polynomial, meaning we are going to get k roots right here. This is just how it works out. now we can bring this into a different form. Remember, we have this right here, okay? Also, we are going to have that x is nothing but, okay, e to the I 2 pi, we know how this works, over 2, okay, kind of. Just a little heuristic approach right here. Meaning, if we cancel out the 2's, we are going to get e to the I pi, but in the complex plane, this is going to evaluate to -1, okay? But also, what else do we have? This is our x1, for example, this negative branch. We also have that x2 is nothing but e to the I 2 pi, okay? Over 2 times 2. This is why our s actually runs from 0 to k minus 1 in this case, okay? Meaning, doesn't matter if you let it run from 1 to k or from 0 to k minus 1, it's going to give it the same thing. This and that is going to cancel out, so this is our second rotation, you could say, and this right here is our first rotation. And this is nothing but e to the 2 pi, e to the I 2 pi is nothing but 1. Okay, I hope you can see where all of this came from. I'm just trying to figure out some examples for you guys. Okay, this was a nice and easy example, but what about x to the 3rd power minus 1? Okay, it's not that easy anymore. Because if you take a look at at x to the 3rd power being equal to 1, well, we can go through the same process, meaning we are going to end up with 3 roots overall, namely x1 being nothing but e to the I 2 pi over 3 right here. This is our k, the k, root of unity. But also, we are going to have the first rotation. This is going to stay how it is. Then x2 is nothing but e to the I 2 pi over 3 times 2 this time. This is going to correspond to our second rotation. Okay, and then x3 is going to be e to the I 2 pi over 3 times 3. Our third rotation, s being equal to 3 right here. Okay, this and that is going to cancel out. On those polynomials, you are always going to get at least one real root. It's going to be 1, e to the I 2 pi. But this thing right here is a little bit more fucked. Because now that we have one root, we can actually decompose this polynomial into x minus 1 times some remainder, some other polynomial, and the roots of this thing are going to be actually imaginary. So it's not as easy as you learned it in school. In school they just say, yeah, all the roots are going to be equal to 1. Yeah, that's the one real root that you are going to get. Okay, those are the cave roots of unity. Meaning we can actually express this polynomial with respect to linear factors, okay? I hope you could follow everything I said. Meaning, going to put it here, x to the k minus 1 power, x to the k power, yeah, minus 1, I'm terribly sorry, I thought I had a typo right there, over x minus 1 is actually nothing but, okay, we are going to have this factor, 1 over x minus 1, I'm going to put it like this, and then linear factors are x minus our first root. So this is going to give us e to the I 2 pi over k, we have a kth degree polynomial, don't forget that, times 1, okay? This is just how it is. Then times the next one, x minus e to the I 2 pi over k times 2. And so on, up until x minus e to the I 2 pi over k times k, corresponding to our kth rotation. And if you draw a little graph, you are going to see on this 3rd degree polynomial, you are going to get branches like this right here. And they actually form a nice polygon all the time, okay? A kth degree polygon. X minus e to the I 2 pi is going to give you 1. That's the reason why I factored out the -1 in the numerator and denominator. This and that is actually going to cancel out. Meaning it's going to leave us with a product running from s being equal to 1, so 1 times this thing, blah blah blah, up until k minus 1, that's the member before our kth member right here, x minus e to the I 2 pi over k times s. And this thing is so familiar. It's just this thing right here, okay? It looks really familiar. One thing that is pretty different is that up here our x is equal to 1. Well, right here this would pose a problem, but we can also look at it from the other side of the medal, namely that this thing is nothing but this polynomial right here. Okay, the simple polynomial. A sum running from s being equal to 0 to k of to k minus 1. K minus 1 was a k minus 1, here it was k minus 1. X to the s power. Don't want any mistakes here. That's so beautiful. I just love this theorem right here. That's just one of the best things ever. Meaning, if you just take a look at this thing right here, why not plug in simply 1? Meaning, we are going to get that this chunk that we also have up here, our desirable thing, is nothing but the sum of 1 to the s power, which is just 1. So that's the empty sum. You can interpret this as being nothing but s 0 to the s power. I'm terribly sorry. No, s to the 0th power. Yeah, it was correct on the first try. S to the 0th power, meaning you are going to get 1 plus 1 plus 1 plus 1. Exactly k times, because if you start from 0, well, then you are going to get, for example, if this runs up until k being equal to 3, so that's a sum running from 0 to 2, so 1, 2, 3, 3 overall. Okay, so this thing right here, this sum is actually going to evaluate to k. Isn't that so cool? Okay, so this weird expression right here actually is just evaluating to k. So our solution to this weirdest trigonometric identity is nothing but k over 2 to the k minus 1th power. Et voila, my sons and daughters. In my opinion, this is an absolutely beautiful result. And I shit you not, this has been the 6th time now that I tried to record this video. Every time I don't know, I just didn't know how to explain it, but this time I'm kind of satisfied with the result, and I hope you are too. If you did enjoy this video, please like, subscribe, recommend, channel, like, and this right here is just a little piece of something that we are going to do soon. An absolutely monster of a theorem, which is just a pain in the ass to prove. I already recorded this video and it was just so exhausting in my opinion. What's going on, smart people? My name Andrew Herbert. If you enjoyed this video, please like, subscribe, recommend channel. Like if you want to support channel a bit more by those details I create, or support channel on Patreon. Up until next video, have a k over 2k minus 1th power day. See ya.